And then multiplying in the front is what's called the universal gravitational constant, which is a very small number. By the way, this is experimentally determined. If you could figure out from first principles why that value is what it is, you'd have a Nobel Prize waiting for you. No one really knows. Okay? But this is the tuning constant for gravity in our observable universe. The way that science has been going lately, the thought is that there are actually a multitude of universes where this value may be different in those other universes. If gravity was much stronger, then everything can never get apart. And if it was much weaker, nothing could ever cohese together. So you can appeal to something called the anthropic principle to say that the value can't be much different from this in order for life as we know it to exist, and the universe as we know it to exist. But nonetheless, no one's exactly sure why this value is what it is. The value goes in the front, and that helps you determine from the two masses involved and their center-to-center separation what is the actual force of attraction. So we've gotten as far as applying it to an Earth and a mass on the surface of the Earth system. Looks like this. We apply the equation. We remember to measure center to center. So the center to center distance basically is 1 Earth radius. That, of course, has to be compatible with what we've been using. And, of course, it helps us to figure out why is the size of the acceleration on the surface of the Earth what it is. So we've known or stated for some time that it's 9.8 meters per second squared. And now we understand that comes from not only the universal gravitational constant, but the intimate particulars of the planet we live on. So the mass of our planet and the radius of our planet are in there. Notice that it does not depend on the mass on the surface, and that, of course, is exactly why all things get accelerated together. So that's something we've noted about gravity since the beginning, right? All objects feel the same have the same acceleration. This law illuminates why that is. It's because if you have more mass and would otherwise be more stubborn to motion, you automatically get more force because you're a bigger participant in the gravity club. So things that have more inertial mass, they're more stubborn to any kind of force, they will also feel more force. So it doesn't have to be this way, but it turns out that gravitational mass and inertial mass are believed to be one and the same thing. So the kind of mass that measures your stubbornness to all forces and the kind of mass that marks your participation in the gravitational club, those are one and the same. So what that means is gravity will pull on you exactly that much harder to make sure you accelerate the same as everybody else, even if you're a big mass. So this tells us why our value is what it is, and it gives us a roadmap to find it what it is in other places. In fact, we could go ahead and we'll stay on Earth, but we'll leave the denominator floating. Okay? So then we can go to various heights above Earth. In fact, we might generically express this distance as radius of the Earth plus whatever height you want to go to. Okay? So it does get weaker with distance. You can see that as you get further away from the center of the Earth, the gravitational acceleration size does decrease. But we just don't notice this because the decrease is very slow. Just to give you an idea, the radius of the Earth, I gave you the exact value before, but that's on the order of 6 million meters. Okay? So let's take the highest mountains on Earth, around 8,000 meters. Okay? So there are 14 mountains in the world that exceed 8,000 meters. None of them even hit 10,000. Okay? So about 8,000 meters. Now how much is really 8,000 adding on top of 6 million? Not much. Okay? So you're going to find that the amount by which the gravitational acceleration is less at the top of Mount Everest is going to be minimal. Maybe instead of 9.8, it'll be 9.79. Okay? If you fall off a cliff climbing near the top of Mount Everest, you will not slowly sail to a soft landing. You're not going to even notice that you're falling to your death and going to die at maybe a millisecond longer than you would have otherwise, okay? So we just don't notice the diminishing of this value, even though it's always diminishing, simply because how much we're changing away from the sea level is really not that much, okay? Even if you go up to like the International Space Station or something like that, you'll find that the gravitational acceleration size is about 90% of what it is on Earth, okay? The reason why they're weightless is entirely due to apparent weightlessness. It has nothing to do with the pull of gravity being very, very much weakened up there, okay? If you really want the force of gravity to get weak, you're going to have to go to very, very significant distances. For instance, if you take this value and you double it, okay? So you are going to go to a height where you basically, you're up here. You have your 1 Earth radius above the surface. You are 6 million meters away from the Earth, okay? That is well beyond space stations, satellites, all that stuff. That's really out there. So you're 1 Earth radius away from the surface, but of course, remember, you should always measure center to center. So you are actually 2 Earth radii away from the center. And you can look at the equation here. And of course, proportionalities, the gift that keeps on giving. Okay, by what factor will the gravitational acceleration size decrease? Anybody? 1/4, right? That's because of the relationship that G and R have to each other, the proportionality that they have. So there, very, very far away, we find that the gravitational acceleration is only 25% or 1/4 of its size that it is on the surface, okay? So it does diminish. It just diminishes so slow that you can't really tell. So certainly for any everyday situations, okay, for all intents and purposes, the gravitational acceleration at the floor level and at the ceiling level of this room is basically constant, although it is technically true that gravitational acceleration is slightly less here than it is on the floor, okay? But we're talking like 1 part per million at that point, so not relevant, okay? We can assume something that isn't really constant to be constant. If that thing that is not really constant changes slow enough, we can ignore those slight changes. Okay, any questions so far? Okay, so now we have the capability to find out how it changes when you're really far away from the surface of the Earth. We can also use the same basic structure to find out what it is in other places. So for instance, on the surface of the moon, all we would do, of course, is we would change out the Earth variables with the moon variables. So G at the surface of the moon, we just do this. So obviously the moon does not necessarily have the same mass nor radius of the Earth. And if you plug in those particulars of that planetoid with the universal gravitational constant, you'll get all of 1.7 meters per second squared, which is not as much. So you've probably seen astronauts on walking around on the moon, okay? They accelerate towards the ground a lot slower, okay? So their spacesuits, which weigh by several hundred pounds, well, they're not really designed to walk around on Earth. You don't need a suit to walk around on Earth. They're designed so you can walk around in a hostile environment. They have lots of life support. So they're very heavy on Earth, but the pull of gravity just isn't as hard on the surface of the moon. In fact, when the astronauts first landed on the moon, they discovered that the normal walking was difficult to do. And the reason why is you inadvertently press too much force against the ground, and when you went to put your next foot down, you missed the ground because you hadn't yet landed. And so they discovered that it's a lot easier to bunny hop. So you've probably seen the astronauts on the moon landing doing that, okay? Because the pull of gravity is much lower. That's about, roughly speaking, about a fifth of of Earth's, okay? So roughly speaking, it's not exactly a fifth, but if I want to refer to it roughly, it's about the fifth of the Earth's surface gravity, okay? At sea level, of course. Okay. So, next thing I want to do, I want to address, so we now have the ability really to find the size of the acceleration due to gravity anywhere we want. We can find it at the surface of the Earth, high above the Earth. Surface of the Moon, high above the surface of the Moon. Mars, Pluto, whatever. Okay? You just need to know the mass and the radius of that planet, and you can get the surface gravity. Next thing I want to talk about is mass versus weight. These are things that are very commonly mixed up with each other, and so it's really important that we keep them straight. I'll explain why they're easily mixed up, but why you really have to be careful. Mass is an intrinsic property. How much stuff something has, that's the same anywhere you take it. It's the amount of stuff. The only way to remove mass is to rip a chunk of the stuff off and take it away. Okay? So, and mass is an intrinsic property of how much stuff an object has. Weight is not. It's an extrinsic property, which means that it's not just the object that defines it, it's something external to the object which defines it. Weight, of course, is another name for force of gravity. The force of gravity on the object. Well, an object can't pull on itself. It's the force of gravity on an object from another object. For example, the Earth. So you can't just talk about the weight of the object in isolation. It's the weight of the object with respect to what? It's the weight of the object when it's being pulled on by something. So we can certainly compute the weight, the force of gravity, by multiplying m times g, as we've been doing. And we can, of course, say, if g is fixed, which it usually is for us, if something has more mass, it has more weight. So if something intrinsically has more stuff to it, it has more mass, then the Earth will pull on it harder. So its weight is larger. That, by the way, is just another statement of this idea that how is it that all masses accelerate the same? Well, it must mean that things that have more mass are pulled harder. That's what weight is. It's just another name for the pulling, the force. And so if something has more mass, it has more weight. If it has more weight, it has more mass. And pretty soon people are just blurring the line between mass and weight, but they are different things. It's just that we're normally accustomed when one is larger, so is the other. So I'm going to show you how you can gain mass and lose weight. Okay? So it's meant to cleave a difference between these two things, so you don't mix them up as easily. And here's my proposal. Here's the Earth. Here's you on the Earth. We're going to put a little space helmet on you because you're going to take a trip. You're going to take a trip to the moon. Okay? And as you take your trip to the moon, you're going to pack yourself some junk food, and you're not going to be able to exercise because you're going to be cooped up in your spaceship. And when you get there, you're going to be looking a little more like this. Okay? So clearly there is more stuff to you. You have gained mass. Okay? So on your trip, you gained mass. Okay. How much there is intrinsically to you has increased. Obviously, you haven't just magically generated mass. It's all that junk food that went in. Okay. So, I'm going to guess that no matter how much junk food you eat, you probably can't make your mass 5 times as much. Okay, that would be a lot. Okay. However, in terms of weight, you might have increased your mass a little bit, but you have hugely decreased the local g where you are. We said that the g on the surface of the moon was about 1/5 of what it was at the surface of Earth. So even the slight mass increase aside, you will still lose weight. Okay? Okay? You've gained mass, you've lost weight. Of course, the trickery is that you take something in the equation which is normally fixed, the g value, and you very purposely decreased it by going somewhere else. Okay? So you've gained mass and lost weight. Okay? So it gets even more confusing when you look at the units. So let's take a look at the units of mass and weight in both SI and in the English system. Okay. So in the SI units, what do we measure mass in? Kilograms. In the SI units, what do we measure weight and indeed all forces in? Newtons. Okay. Okay, so now we get away from SI or the metric system. Of course, we're in this country and we tend to sometimes use non-metric things. English unit for mass. Don't use it. They're called slugs. Okay. Pounds is over here. Pounds is a measure of weight, not mass. So the two things that we most commonly use are actually across categories. Kilograms is a mass and pounds is a weight. Okay? Kilograms is a measure of intrinsic amount of stuff, where pounds is actually a measure of force of gravity. Okay? So we have gained kilograms and lost pounds. Okay? So if you want to advertise your space travel as a diet plan, all the Americans will be very happy because they've lost pounds, and all the Europeans would be like, what do you mean I can eat whatever I want? I'm more kilos than when I left, okay? More kilos, less pounds, okay? So, of course, this is just, we don't normally notice this, that they're different things, because normally G is fixed, and so we don't have to worry about the quantities varying inversely. They both correlate. When the mass is larger, the weight is larger too. But if we wanted to kind of understand this statement, we could say 1 kilogram of intrinsic mass. So when 1 kilogram is 1 kilogram is 1 kilogram everywhere, it weighs 2.2 pounds on the surface of Earth. Okay? And that's when I remember at the very first lecture of the class, I told you that 1 kilogram, if you're trying to get an intuition of that, it's 2.2 pounds, and I put a big asterisk there that's not everywhere, okay? Only on the surface of Earth. It's because they're apples and oranges. They don't have a direct correspondence that you can always count on. it's not like they're both measures of length, right? If the two things are a measure of length, right? 100 centimeters is always a meter. That's true everywhere in the universe, because that's just definitional, right? They're both lengths. But this is talking about a mass and a weight. They're different things. 1 kilogram of mass weighs roughly 1/5 of that, approximately 1/5 of 2.2 pounds, whatever that is, on the surface of the moon. It depends on where you are. The correspondence between pounds and kilograms varies, just like it's a correspondence between how much intrinsic mass you have and how much does it weigh at your local location. One kilogram of mass weighing 2.2 pounds, if we were talking in SI units, we might multiply by a G, so that would be 9.8 newtons. Okay? Those two are apples and apples, okay? 2.2 pounds of force is equivalent to 9.8 newtons of force everywhere. It's just that that amount of force is only generated on this intrinsic mass by the Earth. It's about 1/5 of that when you go on the moon, okay? Are there any questions on that? Okay, so we'll come back to gravity, but for the time being, let's go ahead and seemingly switch gears. We'll talk about circular motion. So now that we have moved into 2 dimensions, obviously this is a type of motion that you can do in 2D that's very particular, and we want to find out what does it take to go in a circle. Going in a circle is a privilege, not a right, okay? A lot of things have to go correctly in order for you to get to do this very special motion. Okay, so let's take a look at what that is. Let me take my object. It'll have a velocity that's some pre-existing velocity. Somehow has that. What does it take to go in a circle? Well, first of all, it's not going to spontaneously do that. In fact, we learned, this is Newton's first law, that if the net force is 0, the velocity is constant. Now, the velocity being constant means not only do you have a constant speed, but a constant direction. So you have to go in a straight line. That's not a circle. So this idea of inertia, this object, any object wants to keep doing exactly what it's already doing if you leave it alone. That means not only having the exact same speed, but also taking the exact same direction it was already moving in and continuing to do that, and that's not a circle, okay? So we have to somehow nudge with a force this thing into a circle. So let me suppose, for instance, that I nudge it this way. I'm going to nudge it to the left. That means that it's going to veer off my straight line path now and move to the left. It's like if you were running down a hallway, right, and someone opened the door and hit you in the side, it would push you over, right? It would deflect you. So this thing is going to deflect like this. Now the moment you leave it alone, so now let's say it has this velocity. The moment you leave it alone, whatever it's doing at that moment, it wants to keep doing for all of eternity. Okay? So whatever is its current state, it wants to maintain that. So if you now release the force, it's going to go like that. And so your job is not done. Okay? You can't just nudge it once and hope that it somehow gets the message. You have to continuously hug this thing into a turn. Okay? So you're going to have to nudge it off that straight line path again. So then it might curve some more. And now that you have the motion like that, The moment you leave it alone, it's going to want to take that exact direction and maintain it for all of eternity. You can see where I'm going with this. You need to continuously exert an effort to nudge it off the path that it's on. And let me just go ahead and finish it up. Don't want to draw it everywhere, but I'll draw it at a couple points here. And if I've done this correctly, which I may not have, let's see. No, these should all point towards a common center. It's not the worst job I've ever done, but it's, so hopefully you drew it better than me. So there's a circle. Those forces should point radially inward. And then the velocity, of course, is tangential to the circle, because that's the direction that it's actually traveling on. So hopefully I've convinced you that there needs to be a continuous